Okay. Well, let's get started. Father, thank you for this day and for all that's happened, good things that have happened since we were here last in this class. Help us to remember things that we need to remember and to cover things that might have in any way been lost and to prepare for a final. Help me to be clear, concise, and thoughtful, and help our students to understand. We pray in Jesus' name. I was telling you last time that apparently the recording cut out.
Yeah.
And since it has been a bit, I figured, well, let's go back and catch just a hair of stuff. And then I promptly left the sheet that I'd written some stuff that I wanted to do on back in the room. But that's okay, we can do this. So we're going to make one up.
Okay.
So let's do CA F2. And let's say that I have let's go for 100 grams of CF2 in let's do 0.93 liters of H2O. Okay, so we're adding this to this, okay? Pure substance, not a solution. It will be once we add it. Now what I want to know is, if I go from freezing to the boiling point, what is my delta T? Now the thing that is important about this is that this is a colligative property and we're dealing with an ionic molecule, so it's going to ionize into 3 species, right? And not just one. I think that's probably the main gist of what was lost on that other video. So if you're catching this now, this is what you missed. So when I put calcium and fluorine in water, it's going to dissociate into 3 things. So the normal freezing point reduction and boiling point elevation that we will see for water, we're going to have to multiply by 3. Right? So, or the effects of it. All right. So one thing I can consider is I have 100 grams of this substance, ionic substance in total, which will tell me how many moles I have of this in total, and then I can multiply that by 3 to figure out how many moles of the solute that I effectually have, right? So first thing I want to do here is probably go, okay, 100 grams times the molar mass of CaF2. So the molar mass of calcium fluoride is, it would be good if I had a periodic table up here, but I don't.
Yeah. Ca is 40.08.
Okay, so 40.08 plus 2 times
19.
19. Okay. So 100 times 40.08 plus 2 times 19. That doesn't seem, that can't be right. That's not right. I did the math wrong. 100 divided by 40.08 plus 2 times 19. Okay, I've got 1.28 moles.
Yeah.
That work for you? Now I need, okay, now I need 3 of these, right? Times 3. So times 3 equals 3.84 moles of solute. Okay. Now I need to find molality, right?
Yeah.
And so to do that,
Divide by the 0.93.
right? I get moles per kilogram. So I've got 3.84 moles. I divide that by 0.93 liters times, I want to take for granted, times the density of this, right? So the density here is 1 liter equals 1 kilogram. That'll put me in kilograms. So when I do that, I get 4.13.
Yes.
4.13 moles. Now, I can take that information and I can begin to plug things in, right? So, my freezing point depression boiling point, I'm going to write both these up here, okay? Boiling point, elevation is KB times M, right? And so my freezing point depression is going to be KF times M. Okay. So we can deal with our freezing point first. I've got, okay. So I need my freezing point depression for water. Freezing point depression for water is going to be 1.86 degrees Celsius per molal, right? And my boiling point elevation factor is going to be 0.512 degrees Celsius per molal. So, dealing with my freezing point, I'm going to go 1.86 degrees centigrade per molal times 4.13 molal, okay? And when I do that,
7.7.
did you get 4.13?
Yeah.
Okay. .6 degrees centigrade. Okay. Now I go ahead and I do the same thing for my boiling point, and I get 0.512 degrees centigrade per molal times 4.13 molal, and I should have like 2 something, right? It's 2.11 degrees centigrade. Okay, so this is essentially, if I were to do a curve of this, or look at a phase change diagram, then I know normally water is frozen at 0 degrees, but this water is not going to freeze until negative 7.6 degrees, right? 7.6. At 7.6 degrees, we are a solid, right? And we remain a solid until everything is melted, and then we will begin to increase our temperature until we reach our boiling point, at which point we're not going to change temperature again until everything's in the gaseous phase. So this is negative 7.6 degrees because our standard freezing point is 0, but our standard boiling point is 100. I'm going to elevate that 2.11, so that's going to make this 102.11. So I just need to know the difference between that, right?
Yes.
And that answer is?
109.71.
109.71 degrees centigrade. That's good. I think I wanted to do another one of this. Who's going to look at this? Will be new for you. Again, I promptly left my sheet in the room, but we'll make one up. I have an unknown quantity of sodium chloride in 0.5 kilograms of water, and it boils at 105 degrees centigrade. I want to know how many grams I have. Okay, so we've got to think about this. It's not too complicated, right? My boiling point is simply my Kb times my molality, right? I know here that Kb times m equals what?
105.
Not 105.
5.
Equals 5. Put 5.0, I should have put 5.0. 5.0 degrees centigrade. So what this is going to let me do is I know this constant, right? So all I have to do is solve for m, and I can work backwards because I have my kilograms of that. So my boiling point constant for water is 0.512 degrees centigrade. So 0.512 degrees centigrade times molality equals 5.0 degrees centigrade, right? So I just divide both sides by 0.512, and my molality equals probably 10 or something like that.
Yeah.
Okay, 9.77 molal. And I know that my 9.77 molal equals the moles of solute over kilograms of solvent, right? My moles, or my kilograms of solvent is 0.5 kilograms, right? Okay. And what I'd like to figure out is how many moles I have, right? And so what I can do is I can multiply both sides by my 0.5 kilograms. So 9.77 moles times 0.05 kilograms is, or I did that wrong, didn't I? 9.77 times 0.5 kilograms equals?
I got 4.885.
Equals 4.885 moles of solute, which in itself does not tell me I can't get to my mass just yet, right? Because?
You need to, because it's 2.
This is ionic, so I've got to divide this by 2, right? And so when I do that, this represents 2 species. Okay? So I divide the whole thing by 2. I'm going to get something like 2.44 moles of NaCl, right? So now I want my mass, so I simply multiply 2.44 times how many grams per mole. How much of this board can I use up? Plus 5. What'd you get?
I got 142.5.
mass of sodium?
I put 23 because it's 22.9.
And then it's 35.5 on the other end.
Yeah.
What number? Try that again. 2.44 divided by. Oh, that's where I'm going. 2.44 times 23 plus 35.5 is 141.5. Good. This is the stuff that's just practical. This is stuff, you know, a lot of stuff we're doing, it's like, it's out there, but in the lab, you start with some unknown solution and you want to know the mass of it. Like, if I know how much I began with when I prepared it, or if I know the molar, you know, I can look at my boiling point elevation. I can work backwards and I can figure it out. So these are just practical steps, even if they're not in your book. There may well be one on your exam. So, all right, we'll go ahead and erase this. Osmosis. So osmosis and diffusion. Osmosis is the movement of, in biology we always learn to say of water, like osmosis is exclusive to water. Your book is saying it's the movement of any pure solvent across a selectively permeable membrane. Osmosis happens just absolutely everywhere in nature. You take one classic thing. You take an egg, you dissolve it in, you dissolve the shell in vinegar. It takes 2 days typically. So the shell is all gone. Now you just got this rubbery membrane there. It's very permeable to water and certain solutes. And you take it and you get some mass, and then you transfer it to a container of water, and you record this new mass. Of course, water is able to move in or out of that egg. Or you put it in with some table salt, and the salt will diffuse into the egg. And then the water will also flow down its concentration gradient and diffuse into the egg because it's selectively permeable. There are other ways of looking at this. There are certainly ways of calculating the pressure with which it moves. So one is this U tube or U chamber. Okay, so we have a selectively permeable membrane here. Well, if I have just pure water on either side, say I started actually like this, right? Okay. Well, I've got atmospheric pressure pushing down on both sides, right? If I leave this for a period of time, these are going to reach equilibrium, right? So they will come out looking like this, right? But now, if I take this, and if this is permeable to water but not to salt, and I put a bunch of salt molecules here. Well, water wants to follow its pressure gradient, right? It will, because it's permeable both ways, right? But these tend to be bound and they're not free to flow this way, whereas these are unbound and they're very free to flow this way. They will. As they do, this side lowers, this side raises, right? And in a vacuum, this would never stop. I'd end up with all my water on this side. But life doesn't happen in a vacuum. And what I'm saying by that is if there's no atmospheric pressure, if that is not a factor, right, then it would just all go. But in reality, we live in a world with pressures, And so perhaps this raises up to here. But I still have some water here, right? Well, when does it stop? The equilibrium is no longer about ion concentrations alone, but it's now osmotic pressure plus atmospheric pressure. Essentially, I have the atmosphere, the gases acting as a piston. You know, I've got osmotic pressure pushing up, and I have atmospheric pressure pushing down. Osmotic pressure wins until we're at equilibrium, until the two are the same. And we calculate that, which is useful. And this has applications in, especially in biology. I'm sure in certain elements of science, of chemistry or physics as well, but big time in biology. Cells are doing this all day, every day, or they die. It's not good for the living thing. So, that was my version of all this. What do they want you to know? Osmotic pressure is represented by pi. Okay, and it's calculated by molarity times the ideal gas constant times temperature in Kelvin. Okay, and the terms for this ideal gas constant, so we have two of these. This one is going to be 0.08206 liters atmospheres over moles degrees Kelvin. And of course, my delta T is my delta C plus 273. The book is having me skip the 0.15, so that works for me. This is easy, which is good. This is fun. It'll get boring after a while, but it's good for right now. So, here we go. Assuming ideal solution behavior, what is the osmotic pressure? So we're going to find P, or find pi. What is the osmotic pressure of a 0.30 molar solution of glucose in water that is used for an intravenous infusion at body temperature of 37 degrees. Okay. So again, this is molarity times ideal gas constant times temperature in degrees Kelvin. Right? So all I have to do is solve for 0.30 molar times 0.08206 liters atmospheres moles degree Kelvin. My molarity moles are a component of this, so that'll cancel out. Now I need to go my temperature. So this is 273 plus 37 equals what, 310?
Yeah.
Right. So 310 times 0.3 times 0.08206.
I got 7.63158.
Yeah, we'll just go 7.6 atmospheres. Okay. Nothing too hard about that. So they want us to do a follow-up question here. Assuming ideal solution behavior, what is the osmotic pressure? So find P, or find pi, of a solution with a volume of 0.750 liters, 0.750 liters, that contains 5 grams of methanol. Which is CH3OH in water. at 37 degrees centigrade. Right, so pi, why do I keep doing that? Pi equals mRT. So first thing I need to do is find my molarity, right? So got 0.75 liters. I got to find my moles. I have 5 grams times 1 mole of CH3OH, which is going to be 32 grams. Now I multiply this all by 0.08206 times my absolute temperature, which is 273 plus 37. That's the same as it was the last problem, so that's helpful. So it's 310 degrees Kelvin, right? Okay. So 5 divided by 32 divided by 0.75 times 0.08206 times 310 degrees Kelvin, and you get
3.97.
That's not what I got.
Let me see what it might be the first. Okay, I think I know what I did wrong. $170.65.
Very final answer. Should be 5.3. And I wrote atmospheres, or liters, didn't I? That should be atmospheres. Let's do this together. So I've got 5 divided by 32 divided by 0.75 times 0.08206 times 310. Yeah.
Okay.
You get it?
Yeah, now I got it. I did the first one wrong.
Okay. No worries. All right.
Just weird on the calculator.
Pardon?
It was just weird on the calculator.
I understand. This next one's going to use a little bit of what we've already kind of been doing. We'll see. Osmotic pressure and changes in freezing point, boiling point, and vapor pressure are directly proportional to the number of solute species present in a given amount of solution. Consequently, measuring one of these properties for solution prepared using a known mass of solute permits determination of the solute's molar mass. Okay. So in other words, if I know how much I put in, and I know what it did to the boiling point or the freezing point or the vapor pressure, then I can determine its molar mass. So a solution of 4 grams of a non-electrolyte of course, again, they keep telling us this to let us know it's not ionizing. We only have to worry about one species. Dissolved in 55 grams of benzene is found to freeze at 2.32 degrees centigrade. Assuming ideal solution behavior, what is the molar mass of this compound? Okay. So we need some information for benzene, which means we got to kind of turn back a few pages that you're not looking at, so I'll give it to you. Benzene's normal freezing point is 5.5 degrees centigrade, and the Kf is 5.12 degrees centigrade per molal. Okay? So I know that my new freezing point is 2.32. It should have been 5.5. I want to see how much it depressed, so I take 5.5 degrees centigrade minus 2.32 degrees centigrade, and I get
318.
how much?
318.
3.18.
Yep.
3.18 degrees centigrade. Okay. So my delta T, my freezing point depression, which is my 3.18 degrees centigrade, right, is equal to my Kf times my molality, right? So my 3.18 degrees centigrade equals my Kf, which is 5.12 degrees centigrade per molal, times my molality, which I don't have
Yeah, you're trying to
just
find.
yet. I'm trying to ultimately work with this. My molality equals my number of moles per kilogram of solution, right? My kilograms of solution is 0.055.
Yeah.
Right. My number of moles,
You don't know.
I don't know yet, right? Have I gone too far ahead in my thinking?
I mean, you can do like that, you're gonna get the answer, you're gonna get the mole right away.
I think I went too far and lost myself in my head. My delta, let's go back to this. Delta T equals Kf times M, right? So my 3.18 equals 5.12 times M. So I can divide both sides by 5.12.
Yeah.
And so what do I get here?
You get 0.621.
0.621
Moles.
is my molality.
Yeah.
Okay. Well, molality equals my moles of solutes over my kilograms of solvent. I want this. This would be really nice to know to get to my molar mass. So I'm going to divide by my kilograms of solvent, which is 0.055 grams. Okay, so this will give me moles of solute, which is
0.034.
0.034
Yeah.
moles. Okay,
You time
I've got
4 grams.
four grams of X equals 0.034 moles of X, right?
Yeah.
So, what do I do? Divide 4 by 0.034,
Yeah.
right? And so what do I get there?
117.647.
Could do, like you said. 11 grams per mole, something like that. All right. Oh my goodness. All right. Okay. Good. We got the same answer they did. I had more to that than I did think, so that's good. Didn't lose myself in the weeds too bad. But let's do another one. Okay. Solution of 35.7 grams of a non-electrolyte in 220.0 grams of chloroform has a boiling point of 64. Has a boiling point of 64.5 degrees centigrade. Assuming ideal solution behavior, what is the molar mass of this compound? Okay. So we got to find out what our information is on chloroform. Chloroform normally boils at 61.26 and its Kb is 3.63 degrees centigrade per mole. Okay. All right. Okay, so we are now boiling at 64.5. So I need to subtract this from that, right? Like, that makes sense.
Yeah.
Oh, yes, it does. Okay, see how. So 64.5 degrees centigrade minus 61.26 degrees centigrade is going to give me my delta T. What is the answer there?
It's 3.24.
3.24 degrees centigrade. Okay, good. Now my 3.24 degrees centigrade, my delta T equals my Kb times my molality. I know what my Kb is here because it's 3.63. So if I divide delta T by Kb, I'll be left with molality, right? So 3.24 divided by 3.63 equals 0.9
Yeah.
moles. Okay. All right. Now, molality equals grams of solute, or no, I'm sorry, moles of solute over kilograms of solution. My kilograms of solution here is 0.220, right? So if I multiply 0.9 times 0.220, I'll get moles of solute.
Yeah, 0.198.
0.198.
Yeah.
Okay. It's giving you 0.198 moles of solute. If I want to find my molar mass, I want moles per gram, I know that I've got 220 grams here, right?
35.7.
Oh, thank you. Thank you. So if I take
Divide 35.7.
by 35, oh, I'm sorry, you were right about that. So if I take 35.7 grams, and I divide it by 0.198 moles, that would give me
180.3.
180.3 grams per mole. How did we do? Let's find out. Lost my page. Yeah, they like that. Good. Okay, what time do we have now there? Okay. All right. Determination of a molar mass from osmotic pressure. So we have 0.500 liters of a sample of an aqueous solution containing 10.0 grams of hemoglobin, has an osmotic pressure of 5.9 torr at 22 degrees centigrade. Assuming ideal solution behavior, what is the molar mass of hemoglobin? Okay. So, pi equals what?
MRC.
Huh? RT, right? Okay. Okay. I know my osmotic pressure, right? So 5.9 torr equals M moles per liter. I don't know that yet.
Yeah.
I need to solve for this right away, right? Times R times T. Do I get to stay with my same R value? They want us to convert right away to atmospheres, right? So when I do that, I can use 0.08206 liters atmospheres per mole degree Kelvin. So yeah, we'll do that. So we're going to go 5.9 torr times 1 atmosphere over 760 torr. All right, so 5.9 divided by 760 gives me
0.007.
0.007
Yeah.
atmospheres. Okay, so that's my pi. And now I can set everything else equal to that. And so what is my everything else?
0.0820 0.26, and the temperature is 295.
My R is 0 point, like you said, 0.8206 times my delta T, which is 273 plus 22 is 294.
95.
95, thank you. Degree Kelvin, right? So, right, when I cross the great divide on this, and I divide 0.007 by 0.08206, I'm going to go ahead and write my next line down here so that we can see it. 0.007 atmosphere divided by 0.08206 times 295 degrees Kelvin. This is going to give me my M. Right, so I do that math, and what do you get, my friend?
I got 2.89 times 10 to the negative 4.
That is different than what our book has. We want to say where they get this. Okay, let me see. We may be off right from the very, very start. So 5.9 divided by 760 equals 0.00. Okay. 7. Let's throw in an 8 here. Okay. All right. So that's our pi. Right. So they want to solve for M, it's pi divided by RT, so we get that divided by 0.08206 divided by 295. I get 0.0003269.
Yeah. 3.2.
Okay, all right, good.
Now I know it's right. I think the 8 made the difference.
Okay. Determine the number of moles of hemoglobin in the solution from the concentration of the volume of the solution. So this is, what do I have here? This is my molarity,
Yeah.
right? I gotta go back. So M equals 3.2 times 10 to the negative 4th moles of hemoglobin per liter of solution, right? So I know how many liters I have,
Mm-hmm.
right? So I want to solve for this. So I divide that by 0.5, right? So 3.2 times 10 to the negative 4th molarity divided by, not divided by, it's times my liter solution. So 0.500 liters of solution is going to give me moles of solute, right? So what does this equal? Should basically
1.6 times 10.
6 times 10 to the negative what?
4.
Negative 4th moles, right? And I know that I have 10 grams. So 10 grams of hemoglobin equals 1.6 times 10 to the negative 4th moles of hemoglobin, right? I want grams per mole, so I divide this by 1.6 times 10 to the negative 4th, and what do I get?
I got 62,500.
6.2 times 10 to the 4th grams per mole.
Yeah.
All right, that is it. I've got to be done.
Mhm.
We'll pick up here next class.